the problem set was like 41 to 62-ish. If we have any questions there, or even things previous to that, we'll start with a chance to address that stuff. Anybody have any questions for Mr. Kulik today? Yeah, Josie.
I have a quick clarifying question.
Absolutely.
So, like, on numbers like 57.
57. Yes.
Do you put the full radian into your calculator? Like, do I put 4 pi over 3 or do I just put 4 over 3?
You'd be in radian mode, and then you'd put 4 pi over 3.
So I include the pi?
Yep.
Okay.
Yeah, you do like 4 cosine 4 pi over 3 and 4 sine 4 pi over 3. But yeah. Or you could convert it into degrees and leave it in degree mode if you wanted to do it that way. Like multiply by 180 over pi.
Okay.
You do it that way.
Yes,
Well, it doesn't have to change your calculator mode jumping around. Sometimes that makes a mess later. Like if you're on a test or whatever and you change it and then you forget to change it back or something.
Yeah.
And
Maybe that was my problem.
yeah. So that's also worth pointing out. Like, yes, you can do it all in the calculator, but you have to be like pretty mode conscious then. Since the previous problems, you were certainly in degree mode to do the story problems, and now you're switching to radian mode, and then if you try to go graph something later, it should be in radian mode, but if you do another story problem, maybe it needs to be in degree mode. It just could be a lot of mode switching, which is fine, but you got to be like aware. If you start getting cuckoo answers, maybe take a look and double check that mode.
All right, thank you.
Yeah, John.
You doing
Sure.
46.
Sure. 46. Okay, it says in question 44, suppose at the exact moment that Matt hits the ball, there's a gust of wind in the same horizontal direction of the ball at a speed of 6 feet per second. Write the new parametric equation, blah, 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 blah. So I'm going to start with what we would have written in for 44. So we have 115 cosine 41t negative 16t squared plus 115 sine 41t plus 3. So all that's changing is that we're adding 6 to the horizontal velocity. So that's all we have to do is update 115 to 121, but only in the x direction, because it says it's horizontal to the direction of the ball that the wind is blowing. So that's all you have to do for part A.
Oh, it's only in the X.
Only in the x direction. Yeah. So there's going to be no change for part B in the value for t. The t will still be the same. When you plug t back in for x, you'll get a different value, right?
Yeah.
But the t here is going to be the same that you got in 44.
I added both velocities.
Yeah, so that's what did it. So the key there in knowing that you're only doing it in that one is it says it's only acting in the same horizontal direction as the ball, so it's only affecting the x component, not the y. So just adding a little push that way. There's no help pushing it up. Yeah. But I think after that, once you make that adjustment, everything, it just works like any of the other problems, so there shouldn't be any problem. Does that feel good?
Yeah.
Cool. Anybody else? Happy to do more if you got more. We can always come back and get things later if you don't have anything at the moment. That's okay. Well, alrighty. Well, let's do the darn thing then, right? Get this show on the road. Today we're going to be finishing up chapter 10. So we're going to look at sections 10.4 and 10.5 today. So in section 10.4, we're going to talk about polar functions in general. One of the nice things about polar functions here, last time we talked about the polar coordinate system and converting back and forth between polar coordinates and rectangular coordinates. Well, it turns out the conversions from polar functions to rectangular functions are the same. So we're using the same information to convert between polar functions and rectangular functions, which is, pretty rad because we just get to double use the same set of information here. So it's no real difference. And that's nice. It's just going to be like how we apply these little theorems or definitions or equations or whatever you want to call it. Okay, so let's take a look at an example. Let's say we're asked to convert the polar function r equals 6 cosecant theta to a rectangular function. How do I know that that's a polar function? Because it's got r's and thetas in it, man. Right? Everybody cool? Okay, typically for a polar function, r is the dependent variable and theta is the independent variable. Okay. So to convert this into rectangular functions, we have to get rid of the r's and thetas and replace them with x's and y's, right? Does that feel good? Okay. So to do this, the first thing I would notice is that my conversion from sines or to get x's and y's, I use sine and cosine, right? So I would first start by rewriting cosecant in terms of sines and cosines. Does anybody remember what cosecant is in terms of sine and cosine? 1 over sine. Yeah, those identities from first semester, do they still matter now? Yes. So far, so good. And I notice now that if I multiply both sides by sine theta, I'll get r sine theta is equal to 6. And what is r sine theta equal to? It's y. Oh, okay. So what does this graph look like? It's a line, right? What kind of line? Horizontal, yeah. So it's just a horizontal line through the y-coordinate 6. So just to kind of show you how we might go about graphing this, I'm going to change into polar function mode. So I press the mode button and I'm going to highlight POL. And make sure I'm in radians. And then I'm just going to press the y equals. And we're going to do 6. And I don't have a cosecant button on my calculator. So I'll just do divide by cosine. And you'll notice when I press the variable button, now I get thetas instead of x's because I'm in polar mode. The calculator does it automatically for me. And then we're just going to do zoom standard. I probably reset my window at some point. Here's my nice horizontal line, y equals 6, like we expected. Okay, well, Mr. Gulick, that's, that's not so bad, right? What if, does this get worse? Well, I mean, there's some other tricks that we need to show you. I don't know how much worse it really gets, but like, let's take another look at another example. We're going to, again, convert this to a rectangular function. Again, by looking at it, it's clear that this is a polar function, right? Since it's in terms of r and theta. So with this one, though, it's a little bit trickier what to do to start, right? If I try to, do the same thing I did before, I'd have to divide cosine theta onto the other side, and r divided by cosine theta is not the same thing as r times cosine theta, so I can't just swap out an x here. Well, maybe we're at a loss. Let's take a look at the picture. Maybe if I look at what the picture is supposed to be, that'll give me some kind of insight as to what to do. So I'll just go back to my calculator, do 6 times cosine theta, and take a look. Huh! What'd I get here? Looks like a circle to me, right? So remember, let's see. The circle for this looks like the center's at 3, 0, and the radius looks like 3 to me also. You guys buy that? So remember, the equation for a circle, x minus h squared y minus, or plus y minus k squared is equal to r squared. So I know the big takeaway here is that the equation that I'm going to write my rectangular function has to have an x squared and a y squared in it. Everybody's cool with that? Well, I know that r squared is equal to x squared times or plus y squared. So I'm going to start by just multiplying both sides of my equation by r. Everybody's cool there? Now, the advantage here is that r squared, if you guys remember, is x squared plus y squared. Right on. And I also notice that I have an r cosine theta, which I remember is the same thing as x. Is everybody okay to there? All right. So I got to make this now look like the equation of a circle. I've accomplished my initial goal, which was to get rid of the r's and thetas. Great. That part's done. If I move everything onto one side, though, I have a little problem with this piece here, right? Somehow that's got to turn into something like x minus h squared. Does anybody remember the name of the process we use for taking something like x squared minus 6x and then turning it into something like quantity x minus h squared? Completing the square. Yeah, good memory. Who said it? Thanks. So I'm just going to abbreviate completing the square as CTS. The idea behind completing the square is we're going to take advantage of the perfect square factoring pattern. So we know that like a plus b squared is equal to a squared plus 2ab plus b squared. Everybody's okay with that? So if we look at x squared minus 6x, we're going to try to make that into a squared plus 2ab plus b squared so we can factor it easily. So my x squared is a squared, which means a is just what? No, x, right? If x squared is a squared, a is just x. So that means that 2ab has to be negative 6x, right? So if I know x is a, then I know that negative 6 is equal to 2b then, right? Everybody's okay with that? if A is x, then negative 6 is equal to 2b. Or just that b is equal to negative 6 over 2. So what I'm going to do then, to complete the square, is I'm going to add negative 6 over 2 squared to both sides of my equation. Luke? You could. I'm going to leave it as negative 6 over 2, so in your notes it's clear where that value is coming from. If I write it as negative 3, which you could certainly do, and you're welcome to do that, or write it as 9, right? Instead of the negative 3 squared, you just write it as 9. That's fine too. I like to write it this way because I think it's clear when you go back and look at it where the heck that thing came from. Is that okay?
Yeah.
All right. So now, x squared minus 6x plus negative 6 over 2 squared, I know how that reduces, or I'm sorry, how that factors. Since it's a perfect square, I know exactly how it factors. It just factors to a plus b quantity squared. Because I made it that. Right? That was the point of the completing the square. So if we just kind of simplify that down. There's my circle with center 3, 0 and radius 3. Does that feel okay? Now, Mr. Kulik, couldn't I have just looked at the picture on my calculator and gone, okay, 3, 0, radius 3, and just gone straight to this instead of having to go through all that completing the square hoopla? Yeah, in this case you could have. Will it always be so clear as to what the center and the radius of the circle are? Nah, man. Let's look at an example where it's a little less clear. Actually, before I do that, I want to ask one more question. Why didn't I do a completing the square on the y squared? Because really I can just think of it as like y minus 0 squared and it's already in the right form. You know what I mean? Since it's just the squared piece, I'm cool. Is that okay? I figured I should at least make mention of that because I'm sure somebody was thinking it. Okay. I'll do one more example of this. And I guess this is as bad as it gets, but if you ask Mr. Kulik, is this even really bad? It's no worse than it was before. God bless you. Sure thing. Let's just start by taking a look at the picture. So negative 5 cosine theta plus 4 sine theta. Okay. Oh, Boise, it's a little bit harder to figure out where that center is. Maybe 2.5 and 2 or something. But then the radius is it's not even really lining up with anything for sure. This is a lot less clear. Turns out that the radius is an irrational number here. So even if you tried, you're not going to come up with the exact value from looking at your calculator screen. You're going to have to do it this way. You could, but it's an irrational number. So good luck coming up with the square root of 41 over 2 as the exact value for the radius there. You know what I mean? You could try. It's not, yeah, it's not going to happen. All right. So what are we going to do? Same thing we did before. Since I know that it's a circle, I know I'm going to need an r squared somewhere. I'm just going to get that r squared by multiplying both sides by r. Oops. So I have x squared plus y squared. I have x, and I have y. Everybody's cool? Just like before, I'm going to group everything onto one side. I'm leaving these big gaps here for a reason, if you're following along. So looks like there's two places where I'm going to need to complete the square. For x squared plus 5x, what do I have to add to both sides to complete the square for that one? 5 over 2 squared. Make sure you do that, add that to both sides. Easy to forget to add it to the right-hand side. And then for y squared minus 4y, what are we going to do to complete the square? Yeah, I'm going to write it as negative 4 over 2, just so it's clear if you're going back and looking at your notes where that number's coming from. But negative 2 squared is the same thing. So for the first piece, if I factor that, that just becomes x plus 5 over 2 quantity squared. For the second piece becomes y minus 2 quantity squared. And then I have 25 over 4 plus 16 over 4. When I add those together, I get 41 over 4. So again, this circle has center 2.5 comma 2, negative 2.5 comma 2. And the radius then would be the square root of 41 over 2. Which again, pulling that from the calculator, not very realistic. You know what I mean? Which is why we're doing it, why I'm showing you how to do it this way. Feel okay? Okay. What if we want to do the reverse direction? What if we want to take a Cartesian equation, a rectangular function, and convert it to polar? So let's say we have y equals 4. Again, you should recognize that as a rectangular function because it's in terms of x and y. Where's the x, Mr. Kulik? Well, it's just write a plus 0x somewhere. You know, like it's there. You just don't have to write it down. Everybody's okay? All right. So the goal to get this in a polar function is we need to get it back in terms of r and theta. Well, the obvious thing to do, we'll take my y and replace it with r sine theta. And typically we write polar equations with the r as the dependent variable, i.e. all by itself. So we can just divide both sides by sine. Or if you wanted to, you could write that as, instead of 4 over sine, you could write it as 4 cosecant. Either is fine. It's not a big deal. If you're looking at a typed solution, I probably wrote it as 4 cosecant because it's didn't have to make a fraction. It's a little bit easier to type it. But that's basically all the reason. Okay. Oh, Mr. Kulik, that was pretty easy. Will they all be that easy? Well, you know, they're all pretty easy, but some of them take a little bit more effort than that. So let's say we have quantity x minus 3 squared plus quantity y plus 6 squared equals 45. And we want to convert that to a polar function. Again, you should recognize that's a rectangular function because it has x's and y's. Even though I agreed it's not a function, but it's a rectangular equation at least, right? Okay. So what do you think we want to do here? What should we do first? Who's my risk taker today? It's no problem if you're wrong. I know a lot of people seem like they know the right answer right away every time, and that's okay. But it's not like nobody's done this before. We're all just kind of guessing. Mr. Kulik knows what to do, and he won't let you go too far down the wrong path without kind of redirecting you. Lily?
Foiling?
Yeah, let's FOIL this out, right? We know that it's, yeah. So if I FOIL this out, what do I get? I get x squared minus 9 plus y squared plus 36 equals 45, right? 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 No! Oh, Mr. Kulik is so sad. What was the mistake? Lily? Yeah, I didn't I just distributed the exponent. I didn't actually FOIL anything. Right? Like, don't make that mistake. It makes Mr. Kulik very sad. He's sad enough, usually, without having to see things like that. Well, I wouldn't let you go too far down the wrong path. Hey, look, after looking at that last set of homework quizzes, we needed to talk about this because I got sad a lot of times because I saw a lot of bad foiling.
What happened with those? The one that really seemed to be getting dropped for the most part.
I don't think so. There's a lot of people got 9s and 10s. Yeah. All right. So we FOILed it out here. Now what should we do?
Get like terms together.
Great. What are my like terms?
Squares, but x. You don't have it.
Lily. How about the 9 and the 36, right? And what I'm really going to do here, I'm just going to put them all on one side. Everybody okay there? What else do you see that we can do here? There's many more things. What's that? We need some R's and Thetas. Great. How are you going to accomplish that?
Well, you can substitute the x's and the y's for like r sine theta,
So you want to take this and make it r cosine theta and this r sine theta?
maybe, but you could do x squared plus y squared equals r squared.
Yeah, let's do that too. And then Luke says I can do this and make that r squared. Oops. This will highlight, right? When I make those substitutions. Does that help if I do that highlight on when I make the substitution so you can see like what's becoming what?
Yeah.
Probably a little bit. At least if you go back and look at this, it probably makes a heck of a lot more sense when you see it. You know? Okay. What do you think now? Okay, so Elvis says to divide everything by r. Is that okay to do? R is a variable. Is it okay to divide by a variable?
No, and you factor out. Absolutely.
In this case, well, let me ask a different question first. I've told you it's not okay to divide by a variable before, right? Why is it not okay to divide by variables?
Zero normal.
It could be 0. Now, r is got to be related to the radius of this circle, right? So can that be 0? No, man. So we're okay. We know r is non-zero, which is great. So we can divide by it, and there's no problem. So all we have to do then is just get the r by itself, which is like trivially easy. And we're done, so. Maybe it's worth kind of checking this. So let's do 6 cosine theta minus 12 sine theta. And take a look at the picture that we get. So that's a circle. Looks like it's at the center is probably 3 over -6 down with a big stinking radius. Looks pretty good, doesn't it? Match what we were expecting. And that's probably about as bad as that kind of a problem can get. Now, well, hold on. For us, let me put that in there. Because we could certainly give you like way worse looking things that are maybe not quite as trivially easy to convert. But really the only conic section that I'm going to use would be a circle. We won't have an ellipse or a hyperbola or something a little nastier in there. But it could be worse, but not for you guys. You know what I mean? And I should say not for you guys right now. Right? Like in future life, you could run into something that's a yuckier conversion than that, but not in this class. All right. So we've talked about how to convert back and forth between rectangular and polar functions. Right? We've talked about how to use the calculator to graph our polar functions so we can have looking at a picture to reference what's going on. What we're going to do now is we're going to talk about some of the attributes that we use to describe graphs for rectangular functions and kind of translate that same thing to these rectangular functions. So we're going to talk about things like minimums and maximums, domains and ranges, and symmetries. So let's say we have the polar function r equals 3 plus cosine theta. And let's say we want to talk about the minimum and maximum for that function. So when we talk about mins and maxes, what we're really talking about is the value of that dependent variable. So it's going to be like some value for r. Okay with that? And if I look at my equation here, my polar function, r is equal to 3 plus cosine theta. So the minimum for r is just going to happen wherever the minimum for cosine happens, right? And the maximum for r is going to happen wherever the maximum for cosine happens. Everybody agree with that? So who can remember the range of values for cosine? Nope. So ranges are outputs. So what are the smallest number that cosine can output? Not 1, -1. And the largest value cosine can output is +1. So my minimum occurs when cosine is -1, and my maximum occurs when cosine is equal to +1. Everybody's okay with that? So that tells me then the range for my polar function just goes from 2 to 4. Those are my values for R. Okay. And then my domain, what is the input for this polar function? It's thetas. So the domain for this polar function is going to be the same as the domain for cosine, because that's all I'm plugging my thetas in is into that cosine function. Who remembers the domain of cosine? What? It's not. It's more than that. We spent all of first semester doing this. It is all real numbers. Yeah. Remember, we spent all of first semester. We started with like cosine and sine in in a right triangle, so from 0 to 90, and we built it out to the unit circle. Okay, 0 to 360, and then we built it out to include everything coterminal to those values, which gave us all real numbers. So you can plug in whatever you want into cosine and sine and cosine, and you get a value back. Yeah, we did that first semester. We spent like 2 chapters kind of building that out. Yeah, it took a while. Okay, but that's the basic gist of it. Does that feel okay? Do you need to see another example of doing this, or you guys feel okay? Well, what's the range for sine? -1 to 1. Yeah, it's the same as cosine. If you think about it on the unit circle, right? You know, like here's cosine's maximum. Here's sine's minimum. Here's cosine's maximum. Here's sine's maximum, right? So it just, everything's -1 to +1 because those are the only values that are only outputs for sine and cosine are the coordinates on the unit circle. The biggest coordinates are going to be at the quadrants. You know what I mean? So they're the same, basically. I guess I didn't need to erase that. Okay. We still need to talk a bit about symmetries. So there's going to be 3 types of symmetries we'll talk about here for polar functions. So we have x-axis symmetry, we have y-axis symmetry, and we have alpha point symmetry with respect to the origin. WRT is just my abbreviation for with respect to. It's a fairly common abbreviation in mathematics. I didn't make it up. So the way that we're going to demonstrate something has x-axis symmetry is we're going to take the r and theta in our equation, replace it with an r and negative theta, and then show that that new equation simplifies down to the original. For y-axis symmetry, we're going to plug in -r and negative theta. And for alpha point symmetry, we're going to plug in theta plus alpha. So let's do an example. Okay, so let's say we're being asked to prove that the polar equation r equals 5 sine 3 theta has y-axis and 120-degree point symmetry. Well, let's just start by looking at the picture, confirm that like when we actually look at the picture, we do see that kind of symmetry we're supposed to, right? Because it's pretty tough to prove something if it's not true. Oops, that was 3 theta. So I'm just going to type in 5 sine 3 theta into my calculator, and I get, oh, it's a pretty flower. So if I look at this, it definitely has y-axis symmetry because the right-hand side of the graph is a reflection of the left-hand side of the graph. Everybody can see that? And it's got 120-degree point symmetry because if I turn this flower 120 degrees, basically this petal is going to be in the same spot as that petal, and then that petal would be in the same spot as that petal, and then that petal would be in the same spot as that petal, and the flower would look identical if I just twisted it 120 degrees. Does everybody feel okay with that? Okay. So I'm pretty convinced that this should be doable because the problem is asking me to do something that's possible. I can see from the picture that, yes, this has both of those types of symmetries. So I'm just going to do this, each of these two proofs separately. Let's do the y-axis one first. To do y-axis symmetry, I have to replace r theta with negative r and negative theta. So I'm going to take my original equation, and where there was an r, I'm going to write a negative r. And where there was a theta, I'm going to write a negative theta. And now what I'm going to do is try to simplify this down so that I end up with the same thing that I started with. So let's simplify inside the parentheses first. 3 times negative theta just becomes negative 3 theta. Everybody's cool with that? Basic algebra there. Now, aha! I see an identity that I can use here. Does anybody see the identity that would be helpful in this situation? I would not use a double or triple angle or angle sum identity, although you could, but boy, oh boy, that's going to get pretty yucky pretty quick. Yeah, I'm going to use the odd-even identity, the one that says sine of negative alpha is equal to negative sine alpha. That's going to be the easiest one to use, which basically just allows me to move the negative sign inside my sine to the front of my sine. Everybody's cool? And if I divide both sides by -1 or multiply by -1, whatever your, whichever your preference, it's doing the same thing. We get the original, so we're done. Yay! Cool? Okay, so to do 120-degree point symmetry, we're going to take r and do nothing, but where I had a theta, I'm going to write theta plus 120 degrees. Let's see, probably start by just simplifying inside the parentheses. So I'll distribute my 3 through. That'll give me 3 theta plus 360. Is there an identity that I could use here? Aha! I see one. Do you see it? This would be the sum or difference identity for sine is what I would use here, yeah. So the one that I'd be using is that sine of alpha plus beta is, well, let's say plus or minus. We'll do the big version. Cosine plus minus cosine alpha sine beta. So that's the identity that I'm going to use. So I get 5 sine 3 theta cosine 360 plus 5 cosine 3 theta sine 360 what should I do next? I see it. Cosine 360, sine 360. Those are just numbers, man. I can use my unit circle or my calculator to compute that. What's cosine 360 equal to? Dude, it's just 1. Right? If I go back and look at my unit circle, 360 is here. X coordinates 1, right? What's sine 360? 0. Wait a minute. Wait a minute. Yes. So I'm just left with r equals 5 sine 3 theta, which is what we started with. Righteous, my dogs. That's pretty neat, right? Okay. So this type of polar function that makes a flower shape. Oops, I lost it. That makes a flower like this. We're going to define those as a whole class of polar functions. These are going to be called rose curves. Now, I've looked at a lot of roses in my day, and most of my roses that I've seen don't really look like that. That looked a little bit more like a daisy or something to me, but like they didn't ask me what to name them when they named them, so I don't get any input, and they just call them rose curves. I don't know why. So the standard form for a rose curve is going to be r equals a cosine n theta, or r is equal to a sine n theta, where n has to be bigger than 1 and an integer. So like n could be 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Okay, the min and max for this is going to just be r equals the negative absolute value of a for the minimum, and r equals positive absolute value of a for the maximum. The domain, since it's only depending on either sine theta or cosine theta, is just going to be all real numbers. The range, because it's just deals with the minimum and maximum, so it's just going to be, the range is going to be from min to max. So negative absolute value a to positive absolute value a. The number of petals is just going to be n, right? Notice that the one we looked at just a moment ago, I saw 3 petals. It was 3 theta. Not a coincidence. And then the last thing is my symmetry. When we deal with rose curves, my alpha is always going to be 360 divided by n. That's how I got the 120 degree point symmetry we were talking about in the previous problem, was 360 divided by 3. So there's 3 situations. If n is equal to even, we get x-axis symmetry, we get y-axis symmetry, and we get alpha point symmetry. So you get all 3 kinds. Whoa! If n is odd and we have the cosine version, we get x-axis symmetry and alpha point symmetry. And then if n is odd, but we have the sine version, we have y-axis symmetry and still alpha point symmetry. And that's easy to remember, right? Because cosine is associated with the x-coordinate on the unit circle. Y is associated with, or sine is associated with the y-coordinate on the unit circle. So cosine going with x-axis symmetry, sine going with y-axis symmetry. That's cool. I like that. So what we might ask you to do with something like this is, like, we might say, like, analyze and then give you some, like, function. So first thing you should notice is that this is a rose curve, right? It's a cosine n theta, where the a is -6 and the n is 5. So my, I don't know, the domain, well, that's easy. It's all real numbers. All the rose curves domains are all real numbers. My minimum value is going to be -6, and my maximum value would be +6. So the range then is going to be from -6 to +6. Okay. I have 5 petals. And I have, since n is odd, and it's the cosine version, I have x-axis symmetry, and in this case, 360 divided by 5 is 72 degree point symmetry. Let's just take a look at this pretty picture and just observe the pretty flowers that we can make. Aw, isn't it pretty? Remember this for Valentine's Day. No? You're like, I can do better than a flower in my calculator. I don't know that you can. I mean, of course you can, but... All right. There is one other class of polar functions that we want to talk about here. So that class is called the Limasson Curves. So that's pronounced Limazon. That's the weird C with the comma attached to it. I don't know what that symbol is called. Somebody looked it up for me second hour and told me what it was, but I forgot already, which says something about my listening skills maybe. It's kind of embarrassing, but I'm willing to tell you guys to show you that, like, Mr. Kulik forgets too. Even things that he was told, like, 24 hours ago. Yeah, I know. All right. So what do the equation look like for a Limasson curve? Well, they're of the form r equals a plus or minus b cosine theta, or r equals a plus or minus b sine theta, where those values for a and b are always considered to be positive. So even though there might be a subtraction symbol in front of the b, we can still consider that a positive value for b, that the subtraction symbol is part of the equation, not part of the b value. Does that feel okay? All right. Domain. Well, shocking, since the function is just depending on sine theta or cosine theta, the domain's all real numbers. Our mins and maxes, the minimum is a minus b, and the maximum would be a plus b. So the range then should be going from a minus b to a plus b. Oh, Mr. Kulik. Of course it would. Now, unique to the Limazon curves, there's actually 4 different types of Limazon curves, and they're all dictated by the relationship or by the ratio of a over b. So if a over b is less than 1, we call that an inner loop. If a over b is equal to exactly 1, we call that a cardioid, because it kind of looks like a heart. You'll see. I think it looks more like a butt. If that a over b is between 1 and 2, we'd say that that's a dimpled. Still looks like a butt. And if a over b is bigger than or equal to 2, we say that's convex. Let me just graph a couple of these different ones for you to give you an idea. So 1 plus 2 cosine theta, a is 1 and b is 2. So this should be an inner loop. And actually, I'm going to turn off the axes to draw these pictures because it'll be a little bit easier to see what's going on. Oh, I'm going to resize my window too. That's kind of far away. Okay. So there's my inner loop. You saw the loop on the inside there that it made. So there's an inner loop. Make that into a cardioid. A and B are both 2. 2 over 2 is 1. So it kind of looks like a sideways heart. Looks a little bit like a butt to me. Okay. Dimpled. So A would need to be 3 and B would need to be 2. So there's my dimpled. Still kind of looks like a butt. The crack there just isn't quite as sharp as with the cardioid, though. It's like the golf ball has the dimpled surface, like the little indents all over it. That's like the dimple you're seeing here. And then we need to do something 2 or bigger, so I'll just make that into 4. And there, I guess some is off there, but you'll notice that there's no indents at all. It's convex. It's like basically kind of looks like a circle. It's not circle shaped, but there's no indents or nothing. Everybody okay? Cool. One more thing to talk about with these Limassons, and that's their symmetries. This is really easy, though. The cosine ones have x-axis symmetry. And the sine ones have, wait for it, Y-axis symmetry? Wowzers! I know, guys, I know. You're so surprised by that. It was like I was leading you one way and then like head faked you and went the other way. Not at all. Wasn't like that at all. All right. Final example for today. Let's just kind of put this together and analyze 4 minus 3 sine theta. This is a Limazon curve where the a is 4 and the b is 3. Notice it's not negative 3. The subtraction symbol is never part of the value for a or b. Okay. So what do we say? The domain, always all real numbers. The min and max, so a minus 3 or a minus b is 1, and then a plus b is 7. So my range then is 1 to 7. The type here, since 4 over 3 is between 1 and 2, we are dimpled. And since we have the sine version, we know that our symmetry is y-axis symmetry. And we can confirm all that by just taking a look at our calculator. 1 minus 3 sine theta. And I think I'm going to zoom standard that because I think it's going to be a little bit bigger. There's my little dimple right there. Still kind of looks like a butt. And yeah, I took the axes off so it'd be easy to see the dimple. What do you guys think? This is pretty easy, right? It's basically just using formulas and plugging and chugging. At this point, you guys can do the rest of the problems in the section, so 63 to 96. The good news is most of these are pretty quick to do. The plan for Thursday is we're going to do our review day. Monday, we're going to start chapter 11. And then Wednesday, we're going to do the chapter 10 test. I chose to start chapter 11 before doing the chapter 10 test because the drama people had a problem with taking a test this week because there's a lot going on this week, which I'm fairly sympathetic to. So A period would have been taking it Friday had we tried to do the test before starting chapter 11. So it just seemed like it would be nicer for all parties involved to just start chapter 11 first and then do the test. That was my reasoning anyways. Everybody cool? Okie dokie. I'm done. So we're going to stop.